Hello everyone. Today let's solve the problem Edgy trees. So this was asked in the Codeforces round 548 division 2, right? So here what the question states. So you can just go through the question. It is very easier to understand. I'll just summarize the question so that it will be easier for us to understand, right? So what the question states here, we are given a tree with n nodes. Just give me a second here. We are given a tree with n nodes and n minus 1 edges. So we are given a tree with n nodes and n minus 1 edges, right? So here it is either colored red or black. So we are given n nodes with n minus 1 edges and it is colored either red or black, red or black, right? And a sequence of k vertices is good if walking through them uses at least one black edge. A sequence of k edges, a sequence of k edges or the k vertices is good if walking through them uses at least one black edge, at least one black edge. So this is very important, right? So here a sequence of k vertices is good if walking through them uses at least one black edge. So what we need to do here, we need to count all such good sequences. So this is good sequence, right? So this is good sequence. A sequence of k vertices is said to be good. See here, a sequences of k vertices is said to be good when it is said to be good if walking through them uses at least one black edge. If walking through them uses at least one black edge. So I can just write here uses one black edge, right? So this is a sequence of k vertices is good if walking through them uses at least one black edge. This part is very important. We have to count all such good sequence and we have to print a result modulo 10 to the power of 9 plus 7 accordingly with the constraint. Just keep this in mind. So we have to print the result modulo 10 to the power of 9 plus 7. Just keep this in mind. We have to print the result modulo 10 to the power of 9 plus 7. So the total number of sequences n to the power of k. Total number of sequence here is n to the power of k, right? So we need to subtract the bad sequences that use only red edges. We need to subtract the bad sequences that use only red edges, or the sequences that use only red edges, right? So that we need to subtract by the total sequence that we got, that we need to extract by the total sequence that we got. Total sequence is nothing but which includes both red as well as the at least one black edge, right? At least one black edge. So that's what they have. This is good sequence basically. So only if we get only red edges, then we have to this one subtract this one by the total, this one, what do we call, subtract this one by the total red edges, right? So total, this one you can call, you can just write it in this way rather than total edges minus red edges. Total edges minus red edges. Total edges is nothing but here this one, which consists of at least one black edge along with the red edge, right? So I hope this part is completely clear. So I'll just read out the question loud. Just try to understand this one, right? So here we are given a tree with n nodes. So we are given a tree with n nodes. Just give me a second here. 1 second. Yeah, we are given a tree with n nodes and n minus 1 edges. Either it is colored red or black. A sequence of k vertices is good if walking through them uses at least one black edge. A sequence of k vertices is good if walking through them uses at least one black edge. So we have to count all such good sequences, right? So we have to count all such good sequences. We have to print the result modulo 10 to the power of 9 plus 7. We have to print the result modulo 10 to the power of 9 plus 7. The total number of sequence is n to the power of k, and we need to subtract the bad sequences that uses only red edges. So keep this in mind. Two things: a sequence of k is good if walking through them uses at least one black edge. This part is very important, and we have to count all such good sequences. So this part is very important, and also we need to subtract the bad sequences that use only red edges. These two things, right? So what we need to count, and we also need to subtract the bad sequences that use only red edges. So a sequence should consist of black and red edge both, at least one black edge, as they have given in the question, right? So I hope the question part is completely clear. right? I hope the question part is completely clear. Just give me a second here. Yeah, so let's come to the example part here. So from this, this is the input basically. From this, we need to find all the good sequences. Means we have to go with a sequence of k vertices that consists of at least one back. This one black edge. So this is nothing but k, and this is nothing but n here. This is nothing but k, and this is nothing but n. Right? K, we know what is k. Right? So n. N is nothing but the number of nodes, nothing but 4 here. So here you can clearly see 4 means we have only 1, 2, 3, 4. 4 nodes will be there, right? So you have to play with 4 nodes itself. You can clearly see 1, 2, 1, 2, 3, 1, 3, 4, 1. So we have only 4 nodes, and K is also 4. K is nothing but a sequence of K vertices is good if walking through them uses at least one black edge, at least one black edge, right? So here k is 4, n is also 4, this part, and the output for this one, this input we need to get 252, right? Same goes with this one as well, this input and this input as well. You can just look at it in the same way. So let's consider this first example of the first input in the question, so that it will be easier for us to understand with the help of the approach. So for the approach, I'll just consider this first example, right? So I hope the input output part is completely clear, man. So we have not yet discussed the approach part. So through the approach, you'll come to know how we got this one output, as well as what is the this one data structures and other stuff that we'll be using, right? So to write the code mainly. So I hope this part is completely clear. Question part is completely clear along with the this one. What do we call examples, right? That they have given. Now let's discuss the approach followed by the complexities, and then let's write the code. First, let's discuss the approach. So here I have considered the same first example that they have given in the question, right? So this is nothing but the n and k. Initially we have n and k. N is 4 and k is also 4, right? According to the first example that we have already discussed this one. So this is nothing but n, and this is nothing but k. Both we have 4 here. So these are the edges. So number of nodes we have is 4, right? So here you can clearly see 1, 2, 3 and 4. So basically we have 4, n is 4 and k is also 4 here. The output that we need to get here is 252 accordingly with the question. Let's see the step-by-step explanation here. So here we have n equals 4, nothing but we have 4 vertices, and k equals 4. We need to find the total good sequence of length 4. We need to find the total good sequence of length 4, right? So all the edges are black here. Means at least one edge has to be black, right? So here the formula that we have already discussed is good equals total sequences minus bad sequences. So this one we have already discussed in the question. Good equals total sequences minus bad sequences, right? So let's come to the next step here. So we have to count the total sequences. We can choose any of the n equals 4 vertices, right? So we can choose any of n equals 4 vertices for each of the 4 positions, for each of the 4 positions, right? So this will be we have n equals 4, right? We have number of vertices as uh, nothing but number of vertices or nodes or edges is nothing but 4, right? For each of the this one, what do we call, for each of the 4 positions. So we know that this is n to the power of k. This is nothing but n to the power of k. Total formula is nothing but this one, n to the power of k, right? So n we have 4, n we have 4, right? Number of vertices, and k also we have been given 4 in the input. So 4 to the power of 4 will be 256, will be 256. Now we have got the total vertices, that is not total sequences, nothing but the 256. So we have to subtract the bad sequence. Means in this case we have to subtract only with the red edges, only with the red edges. Bad sequences is nothing but uh, it consists of only red edges. It doesn't consist of the black edges, right? Accordingly with the question. This one we have discussed already. So we have to identify only red only components. Now we build a graph using only red edges here. Xi equals 0, but here all the edges are black. So no red edges exist here. no red edges exist. So the red only graph has four isolated nodes, meaning each node in its own component of size 1. So here, so the red only graph has four isolated nodes, meaning each node is its own component of size 1. We know this one, right? So here, uh, so the bad sequences we can write in this way: 1 to the power of 4 4 times, right? 1 to the power of 4 4 times. Why we have considered 1 here? So we have already discussed this one. Basically, red only graph has four isolated nodes. Four isolated nodes, meaning each node has its own component of size 1. Size 1. This part is very important. So here we are going with 1 to the power of 4 4 times. 1 to the power of 4 4 times, nothing but 4. So anything to the power of 1 will be 1 itself, right? So here in this case, these are the sequences that can be written like this: 5 times 1, 4 times 2, 4 times 3, and 4 times 4. So they are not good because here they don't move through any edges. Though they don't move through any edge here. This one, 5 times 1, 4 times 2, 4 times 3, and 4 times 4. They are not good because here they don't move through any edge. So no black edge is used. No black edge is used right here. They are not good because they don't move through any edge. So no black edge is used here. No black edge is used here. So we have to subtract 4 from 256, right? So 256 is the total sequences, and 4, uh, we got this one bad sequences. 4 means only red edges, right? So we have to subtract the bad sequences from the total sequences. Here in this case, good equals total minus bad, right? So we have already discussed this one. This is nothing but 256 minus 4. This will be 252. So the final output that we got here is 252, which is equivalent to the output that they have given for the example 1 in the question, which is equivalent to the output that they have given for the example 1. So our approach works absolutely correct in this case. As we are completely familiar with the approach, let's do one thing. Let's discuss the complexities, right? So let's discuss the complexities here. So what will be the time complexity here? The time complexity would be big of n plus k logarithmic n. Big of n plus k logarithmic n. So why it is n plus k log n here? Because we will be going with reading input, building graph, and also we'll be making use of the approach DFS. I didn't mention, sorry, this one. So we will be going with the DFS approach. Basically, overall time complexity would be big of n plus k log n, because we will be going with reading input. This one we will be going with a reading input, and also we will be going with building graph here. We'll be going with building graph, and the third one will be making use of the DFS, and also we will be going with the mod power calls. This one, mod power calls, right? So these four things will yield us to the total complexity, time complexity of big of n plus k logarithmic n. So why the space complexity here is big of n? Because we'll be going with a graph, right? So we will be building the graph basically. Also we'll be making use of the visited. Visited means we shouldn't reuse the same nodes. We shouldn't reuse the nodes that has been visited, already visited, right? So that is the reason we'll be going with a visited, right? Also we'll be going with a DFS stack. Also we'll be going with a DFS stack, which will give us the overall space complexity big of n here. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n plus k and big of n. This one I'm speaking of. This part I'm speaking of, right? So I hope this part is completely clear. Just give me a second here. Yeah, I hope this part is completely clear. Now, as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. So we'll be making use of the fast input and fast output. For that, we'll be going with the buffer data, and also we'll be making use of the this one utilities, different utilities. So we'll be going with the input output as well as the utilities package. So I'll just go with here import java.io.star. This is fine. And also import java.io. util dot star. This is fine. So here let me go with class main. So I'll just go with here class name main. Within this class, uh, so they have given the mod value, right? So we have been given the mod value 10 to the power of 9 plus 7. So let me do one thing. I'll just go with static final int mod. Let me assign this one to the 1000, this 1007. This is fine. So the next step is let's build the adjacency list for the red only edges, because we have to subtract that one finally from the total sequence rest, right? So let's build the adjacency list. First we have to build the graph, and write out the graph, and then we have to build the adjacency list out of the graph for only considering only red edges. So I can just write it in this way. This would be static list. So this will be integer, and here this would be red graph, red graph, right? So this is nothing but the adjacency list for red only edges. Next, let's do one thing. This will be static boolean. So let's consider the variable visited here. So this will be static int k. So we are done with this part. Next, let's do one thing. Let me give main here. So yeah, let me delete this one. Also, let's make use of the input output exception, or else we'll get the error. So I'll just go with here input output exception. This is fine. So let's do one thing. First thing, as I've said, we'll be making use of the fast input, right? For that one, I'll just be going with the buffered radar here. Buffered radar. Let me assign this one to the new buffered radar input stream radar system dot in. This is fine. So the next step here would be print radar. This one will be what equals new print radar system dot out. So this is fine. Let me come out of this one entirely. So now we have to read the number of vertices, and this one n and k, nothing but number of vertices and length of the sequence as well. For that one, let's do one thing. Let's make use of the string tokenizer, right? So I'll just go with string tokenizer st equals new. So this one will be string tokenizer buffered radar dot read line. So this is fine. Next, let me assign n to integer dot percent st dot next int. This is fine. Next, this will be next token basically. This is fine. Next, let's assign k to same thing here, integer dot percent of string tokenizer dot next token. So this is fine. So let me come out of this one entirely. Let's initialize the read only graph. Means we have to find the read only edges. To find the read only edges, we have to initialize the read only graph, right? So here this would be red graph equals, let's make use of the array list. So I'll just go with new array list of n plus 1. This is fine. The next step is, let's go with the simple for loop here. Int I equals 1, I less than or equal to n, I plus plus. So this will be red graph, iterated value of the red graph equals new array list, new array list. So this is fine. So now we have to build red only graph, nothing but we have to add the edge if color equals 0, nothing but if color is red. So let's go with the simple for loop here again. Int I equals 0, I less than n minus 1. Let's increment the I. Within this for loop, let me assign the string tokenizer to mm, string tokenizer. This is fine. Buffered reader dot. Let's make use of the uh, we have to go with we are reading right here input, so I'll just go with the read line. So this is fine. So the next line is we have to calculate the this one, right? What do we call adjacency list? So we have to build read only graph here. Means we have to add the edge if the color equals 0, nothing but if color is red, then only we have to add that particular edge. So we have to subtract that one from the total subsequences, right? So that is the reason. So here this would be int u equals integer dot parse here string tokenizer dot next token. This is fine. Let me do one thing. This will be int v equals integer dot parse here. So this one will be string tokenizer dot next token. So this is fine. So next, let me assign the color to. So this one will be integer dot parse string tokenizer dot next token. So this is fine. So here next step, if the color equals 0, then only we have to add that particular edge. Means if we are building the read only graph here, only we have to add the edge if the color is 0 or if the color equals 0 in comparison. Means if color is red, then only we have to add that particular edge. Let's write that condition. So here if color equals 0, then what we need to do? So this will be red graph of u dot add of this one v. This is fine. Again red graph of v dot add of this one u. So I hope this part is clear. Let me come out of this one entirely. So now let's make use of the variable visited, right? So here I'll just go with the visited and let me make use of the boolean here, boolean n plus 1. So we don't have to visit the nodes that we have visited earlier, right? So total possible sequences we have, we know this one from the approach, nothing but n to the power of k, right? N to the power of k. In our case, n was 4 and k was 4, right? So total possible sequences that we need to go with n to the power of k. For that one, let's do one thing. Let me assign the total to mod power of n comma k. So we will be calculating mod power this one. We have not yet written this method yet. So we'll be writing this one in the future, right? So let's do one thing. Also, let me assign bad to 0. Bad to 0. This is fine. So the next step here would be for each connected read-only component, we have to calculate bad equals sum of component size to the power of k. For each connected read-only component, we have to calculate bad, nothing but sum of component size to the power of k. So this will be for int I equals 1, I less than or equal to n, I plus plus. So this is fine within the for loop. If not of visited, if not of visited of I, so this one within the if condition, what we'll do, we have to find the size of connected read only component, right? So I can just write or articulate in the form of code in this way. This would be size equals dfs of I, dfs of I. So this is fine. So next is bad equals, so here it would be uh, bad plus sorry, not madman, mod, right? Mod power. So yeah, mod power of size comma k, size comma k modulo mod. So we have assigned the mod to this one, 10 to the power of 9 plus 7 we are making use of right here, this one, 10 to the power of 9 plus 7, sorry. So this is fine. Let me come out of this one entirely. So let me do one thing. Let's go with, so again I'm telling, so I'm just writing the code directly here. In this case we have not made use of this one. Where did I use DFS? We have not performed DFS yet, so I have directly made use of the DFS method directly here, right? So we will be writing the helper method, this one, helper function DFS again. So we have not written helper function DFS as well as the mad power, this one mod power, right? So this one will be writing in the future, so I have just made use of this one directly. Don't get confused here, right? So this is fine. Next, let's do one thing. We have to go with the good sequences equals total minus bad, right? So that is the formula that we got. So here in this case, let's go with the good sequences, nothing but here total minus bad. So I'll just go with long good equals total minus bad plus mod, this one modulo mod. So this is fine. So this will be out dot print, oh, print gives this one, so sorry, print ln of good, right? So good sequences, that's what we need to print here. Basically we are about to end the program, but we are at the end of the code, but we have not yet written the DFS, and I have written this one directly, helper function DFS and mod power, right? So this one we have to write this one yet, right? So I should have written that one and then made use of it in the main function within this function, but uh, I wrote this one. We cannot do anything now, so let's do one thing. So let's this one, I'll just make use of the out.flush here. So now we are done with the code. Basically now let's write the this one. This has to be out dot println, right? So why it has become like this? So this will be out.println. So this is fine. So let me come out of this one entirely. So what shall we do? Let's go with the standard DFS or the depth first search to count the size of read-only connected component. So I can just write it on this way: static int DFS, right? Static int DFS. So let's go with the this one in node. So we are just passing the node as parameter. So to perform the DFS, let me make use of the stack here. So we will be going with the stack. So here this will be iterated DFS, right? So we are not going with the recursion. We are basically going with the iteration, DFS with iteration. So here in this case, stack, let me go with new stack. This is fine. So the next line would be, this has to be capital I, man, not the small I. This is fine. So the next line would be stack dot push of, let's pass the node here. This is fine. And also let's go with the visited of a node. Let's assign this one to boolean value true initially, and also we need the size. So let's assign the size to, I mean, let's initialize the size with 1, right? Initialize the size with 1. So let's go with the this one. Let's move on with the further steps here. So pure DFS here in this case, when the stack is not empty, means it has to contain certain values, right? So when it is not empty, we have to move on with the certain further things, right? So that is the reason we have written this one within the while loop, right? So this is fine. We are just making use of the isEmpty operation that the stack provides. So let me do one thing. Let's make use of the u and assign this one to the stack dot pop. This is fine. So let's go with the for loop here. This will be int v, the red graph, this one u, so we have considered u, I think, right? Yeah, this is fine. So here within this for loop, if we have not visited any edge, then we have to visit the neighboring edge and mark that one as the boolean value true, right? And then we have to increase this one, increment the size, and we have to push that vertex. After this one visiting, we have to push that edge, right? So that's what we need to do. Let's write the simple if condition here for that. So this is simple, man. So I'll just go with if not of visited of, v here. So here this will be visited v. This one, let's assign this one to the boolean value true, and let's increment the size, and also stack dot push this one. Let's push the v, right? Edge or the let's push v here. This is fine. We have considered v, right? So this is fine. Let me come out of this one entirely. So we need to return the size, right? So we are calculating the size. So we are performing DFS to calculate the size itself, right? So we are done with this part. We are done with this part. We are only left with this one mod per this one mod power helper function. Means we are making use of the mod power helper function for the fast exponentiation, right? So nothing but base to the power of exponentiation modulo mod. So this one, rather than telling this one, let's write the this one helper method, so it'll just come to know. So this will be not stack, so let's go with the static here. Long long this one will be mod power. So this one will be long base, comma, in exponent. So this is fine. So let me assign the result to 1. This is fine. Base modulo equals mod. This is fine as well. So here exponent has to be greater than exponentiation has to be greater than 0, right? It has to be greater than 0. So while I can just write exponentiation has to be greater than 0, I'll just consider exp here. So in this case, when it is greater than 0, let's write the simple if condition here. So exponentiation logical this one and 1, this one, if it is equal to 1. So let me assign result to result into base this one modulo mod value. So it is 10 to the power of 9 plus 1, 9 plus 7, right? So this is fine. So let's assign base to the formula base into base. So this one modulo mod. This is fine. Uh, let's go with the exponentiation here. Right shift operator equals 1 equals 1. And final step here would be we have to return the result. We have to return the result, right? So we have considered the result variable here, and initially we have initialize this one to 1. Finally we have to return the result. This is fine. So we are done with the code. We are done with the code. Before trying whether this code works or not with the particular inputs, let me do one thing. Let me paste the signature starter template, right? So let me come here. Let me give this, ignore this one. So just let's concentrate on the this part, logical part basically, right? So let me come here. Let's copy the input and let me paste it over here. So this has to give us the output 252. Let's see. So what error we have? Warning unchecked conversion. This is fine. Let's ignore the warning. How many errors we have? 3 errors. So let's concentrate on the errors here. Cannot find the symbol boolean. Boolean we have mentioned misspelled here. Boolean. Line number 46. So let me come here and just give a. This is fine. The next part is new symbol variable. What? Oh, this one total. This one also I have misspelled here. Line number 58. So let me come to the line number 58 here. This has to be total. This is fine. And let's come to the final part here. Cannot find symbol. Dot flash. Huh? So let me run this one first. So we have n one error. Dot instead of the flash I have given I here instead of L. So let me make this one L. So let me run now. We have to get 252. Yeah, we are getting the output 252, right? So this works absolutely correct. So let's try it out with the different inputs. So here just ignore the warning. This is fine, man. This works absolutely fine. I hope this works with the Codeforces environment. Let's see. So here, if I run, so yeah, we are getting the output 0, correct output, right? So let's go with the final this one input. So we have to get the output 210 here. Let's see. We paste this one and run the code. Yeah, we are getting the output 210. So the whatever the code that we have written works absolutely correct for the inputs that is mentioned in the question. So let's see whether this works for all the test cases or not. So let me copy this one entirely. Let me come here. So I have already selected this one. See this one, Edgy trees. So let me paste the code and let me hit the submit button. I hope this works for all the test cases, man. Let's see. So let's wait for some time. You can clearly see here running on test 2, test 4. So yeah, you can clearly see here all the test cases are getting passed, means the code got accepted, right? Means whatever the code that we have written works absolutely correct, right? So whatever the code that we have written works absolutely correct. Now, as we are, just give me a completely, just give me a second here. This is- Yeah, this is fine. I hope whatever the solution that we have written is completely clear, right? Along with the complexities and the approach. For now, this is it. Thanks for watching, guys.